Hello everyone, myself Soumya Vijay, Assistant Professor, Department of ECE, SJBIT. In this session, I will be discussing about the Module 2 topic of microwaves and antennas. The Module 2 is about microwave network theory and passive devices. In the Module 2, I am discussing about microwave passive devices. The microwave passive devices can be listed as coaxial cables, attenuators, phase shifters, waveguide T's. In waveguide T's, E-plane T, H-plane T and magic T. Let us first discuss about coaxial cables. The microwave passive devices and components are designed using sections of the coaxial lines, waveguides, strip lines and microstrip lines for use in both laboratory and in microwave communication and in radar systems. It means whatever microwave passive devices and components we design, they are being connected by means of sections of coaxial lines, waveguides, strip lines and the microstrip lines, and their usage is in laboratory as well as in different microwave communication and radar systems. These components can be considered as one port or multi-port networks, and they can be characterized by basic parameters like VSWR, reflection coefficient, and there may be various losses under output matched conditions. A coaxial cable is used for interconnecting several microwave components. In the coaxial cable, as we already know, there will be a two conductor, one is inner conductor, another one is the outer conductor. The outer conductor of the coaxial line is basically used to guide the signal through TEM mode, transverse electromagnetic mode, and it will sheet the external or internal signal leakage that happens through it. The standard characteristic impedance of these cables will be 50 ohms and 75 ohms. Based on the increasing order of the shielding, we can classify these coaxial cables as three basic types. One is flexible, semi-rigid and rigid. Coming to the flexible coaxial cables, they use low loss solid or foam polyethylene dielectrics. And in this case, the outer single bride or double bride of the flexible cable is mainly constructed for electromagnetic shielding, and that is done by using knitted metal wire mesh. And coming to the rigid cables, in the rigid cables we have air as dielectric, and the conductors are actually supported by small dielectric spaces such that they do not produce significant discontinuous to the signal flow. And coming to the semi-rigid cables, these semi-rigid cables have solid dielectric and they use a thin copper outer conductor so that it can be bent for convenient routing. These coaxial cables are used in the frequency range from DC to microwaves. They can be used from DC to microwaves since the attenuation in these cables increases with the frequency. I repeat, the coaxial cable is basically used for interconnecting several microwave components. The outer conductor of the coaxial line is used to guide the signal through TEM mode and shield the external or internal signal leakage through it. The standard characteristic impedance of these cables are 50 ohms and 75 ohms. There are three basic types of coaxial cables with increasing order shielding, that is flexible, semi-rigid and rigid. Flexible coaxial cables use low loss solid or foam polyethylene dielectrics. The outer single bride or double bride of the flexible cable is constructed for electromagnetic shielding by using knitted metal wire mesh. And the rigid cables have air dielectric and the conductors are supported by small dielectric spaces such that they do not produce significant discontinuous to the signal flow. Coming to the semi-rigid cables, they have solid dielectric and they use a thin copper outer conductor so that it can be bent for convenient routing. And these coaxial cables are used in the frequency range from DC to microwaves since the attenuation in these cables increases with the frequency. These are the three coaxial cables, flexible, semi-rigid and rigid. This is the flexible one, this is the semi-rigid one, and this is the rigid one. As we can see, this is the center conductor and this is the outer conductor, and this dotted line represents the dielectric spaces. And coming to this case here, center conductor and this is the braided outer conductor, this is the dielectric core and this is the insulating jacket. And coming to the some standard coaxial cables tabular representation, this is the number of the coaxial cable and this is the impedance in ohms and this is the inner and outer conductor, what it is made up of, what type of metal we use. For example, if I go for 9 bar U number of coaxial cable, the impedance is 50 ohms and the inner or outer conductor is made up of silver plated copper. For 11 bar U, it is 75 ohms and they are using tinned copper. For 58 A bar U, the Z0 is 50 and inner and outer conductor is again made up of tinned copper. For 59 bar U, it is 75 ohms and inner and outer conductor is made up of copper. For 141 A bar U, the Z0 is 50 ohms, inner and outer conductor are silver plated copper. Next is 179 B bar U, Z0 is 75 ohms and inner and outer conductor are silver plated copper. 214 bar U, Z0 is 50 ohms, inner and outer conductor is silver plated copper. Now let us discuss about the coaxial connectors. This table 2 represents the different coaxial connectors, the type of the connector, fine, and what is the meeting connector it is, what is the type of meeting connector and the dielectric in meeting space and what is the impedance here. These are been the diagrams, pictorial representation with respect to this is also shown here. The first one is N type, which is called as navy connector. This can be used as either male or female connector and the air is a dielectric and the impedance is 50 or 75. Next is BNC connector, this is again male or female connector, dielectric is solid and the impedance is 50 or 75 ohms. Next is the TNC connector, it is again male or female connector, dielectric is solid and again impedance is 50 or 75 ohms. Coming to the next connector, SMA connector, again this is male or female connector, the dielectric is solid and the impedance is 50 ohms. Next is APC 7, this is a sexless meeting connector and the dielectric is here and the impedance is 50. Next is APC 3.5, this is a sexed connector and the dielectric is here, impedance is 50 ohms. Now let us know each connector in detail. Coming to the first type, that is a type N navy connector. It is a 50 ohm and 75 ohms connector, which was basically designed for military system applications. It was basically used for military system applications and it was designed for 50 and 75 ohms. And this is suitable for flexible or rigid cables in the frequency range of 1 to 18 gigahertz. Next we have BNC connector, Bionit navy connector. Bionit navy connector. This is having a dimension of 0.25 inch and the impedance is 50 ohms or 75 ohms and it is a flexible cable which is used up to 1 gigahertz. Next is the TNC, threaded navy connector. It is same like BNC except that the outer conductor has a thread in order to make firm contact in the mating surface. Mainly this is done to minimize the radiation leakage at the higher frequencies and these connectors are used up to 12 gigahertz. The next type is SMA sub-miniature A connectors, which are used for thin, flexible or semi-rigid cables and the higher frequency is limited up to 24 gigahertz. Next we have APC 7 Amphenol precision connector, which is having 7 millimeter, is a very accurate 50 ohms low VSWR connector and it can operate up to 18 gigahertz. Next we have APC 3.5 connector. It is a high precision 50 ohms low VSWR connector and it can be either male or female and it can operate up to 34 gigahertz. The second one is BNC with 0.25 inch, 50 ohms or 75 ohms flexible cables up to 1 gigahertz. Third one is TNC, threaded navy connector. It is like BNC. The outer conductor has a thread to make firm contact in the mating surface to minimize radiation leakage at higher frequencies. This is used up to 12 gigahertz. Next is sub-miniature A. For thin, flexible or semi-rigid cables it is used. Higher frequency is limited to 24 gigahertz. Next is APC7 Amphenol precision connector 7 mm, very accurate 50 ohms, low VSWR connector, operate up to 18 GHz. Next is APC 3.5 connector, high precision 50 ohms, low VSWR connector, either male or female it can be, and operate up to 34 GHz. Let us now discuss about the attenuators, the next passive device. The attenuators can be defined as the passive devices which is used to control the power levels in a microwave system, and this has been basically done by partially absorbing the transmitted signal wave. So, what is the definition for the attenuator? Attenuator are passive devices. They are used to control the power levels in the microwave system, and that is done by partially absorbing the transmitted signal wave. Both fixed and variable attenuators are designed using resistive films, because the main element that is present in the attenuator for partially absorbing the transmitted signal wave is resistive film, which is an aqua coated dielectric sheet. Now, first let us discuss about the fixed attenuator. A coaxial fixed attenuator uses a film with losses on the center conductor to absorb some of the power. A coaxial fixed attenuator, it uses a film with losses on the center conductor to absorb some of the. Next, the fixed waveguide type consists of a thin dielectric strip coated with resistive film and placed at the center of the waveguide parallel to the maximum E field. One more, the induced current on the resistive film due to the incident wave results in power dissipation, which in turn leads to attenuation of the microwave energy. The dielectric strip is tapered at both ends up to a length of more than half wavelength in order to reduce the reflections. As we just get a reflection which is reduced, so that is been tapered, and what is the amount of tapering is to a length of more than half wavelength. And the resistive vane is supported by two dielectric rods separated by an odd multiple of quarter wavelength, and which is perpendicular to the electric field. As you can see here, the first one is the coaxial fixed connector. There is a lossy material on the center conductor of this coaxial attenuator. This is mainly used to absorb some of the power. As you can see here, this is one more type in which there is a resistive film that is placed here. This actually can be called as a variable attenuator as well, because by turning on the screw we can move this resistive film narrow to the wall, or it can be brought to the center, so that we can get the maximum attenuation there. Noticed here in this dielectric strip has got a tapered section. Why the tapered section is mainly in order to, you can notice in this figure B. Coming to the variable type attenuator, as I told, this is the second one, can be called as a variable attenuator here. It can be constructed by moving the resistive vane. This is the resistor that is moved by means of a micrometer screw from one side of the narrow wall to the center. From one side of narrow wall to the center it can be moved, and when it is moved to the center, the E field will be maximum and the attenuation will be more. Or one more type is there in variable type attenuator, which is called as flap attenuator. This is a variable attenuator again. Here, by changing the depth of insertion of the resistive vane at an E field maximum through a longitudinal slot at the middle of the broad wall, we can achieve the maximum attenuation. Here the changing this is the attenuator flap, this is the hole of the insertion here, and this is in the form of a conical shape, and as this attenuator flap is being pulled towards this hole, okay, it is being pulled through the longitudinal slot at the middle of the broad wall, and as it goes deep inside, the attenuation is more, and as it is slighter, the attenuation will be less. And in this case, the maximum of 90 dB attenuation is possible with VSWR of 1.05. As well, the resistive card can be shaped to give a linear variation of attenuation with the depth of insertion. As the depth of insertion increases, the resistive card we get the more variation. So, this is actually dependent on what the resistive card. So, this resistive card is the one which can be shaped to give a linear variation of attenuation with the depth of the insertion. This is about what is attenuator and what are the two basic types of attenuator, that is fixed attenuator and the variable attenuator, how actually the construction is being done with respect to these two attenuators. In the next session, I will be discussing about the one more important type of variable attenuator, which is called as precision type variable attenuator. Thank you. Thank you.